Today we'll be discussing our project on activation checkpointing in Neal. So the idea here is if we have some fixed memory budget, we might not want to store all the activations that we took during the forward pass, and only rematerializing those intermediate tensors when they're needed to propagate gradients on the backward pass. Of course, being careful to delete these rematerialized tensors so that we don't go over our memory budget. So this allows for sublinear memory costs, linear in the size of the computational graph, and allows us to trade off memory and compute. So some implementation details on what we've implemented so far. One of our strategies was a layer-wise checkpointing, where during the forward pass, given some layer that's not checkpointed, we collect all of its intermediate tensors, and then iterate over all those intermediate tensors and delete their cache data if some conditions are met, which I won't go into now. Subtlety here is that this DFS call looks like it might be expensive, but instead we keep a running visited set that stores all intermediate tensors so far in the computational graph. That way, this DFS call for a given layer will only touch the intermediate tensors of that layer, as opposed to needing to go all the way back through. And so overall, we only need to touch each intermediate tensor, one time extra.
On the left, we see an example of the usage. The layer-wise checkpointing only requires adding the two lines in red. The patcher replaces any NN sequential instances in the model with a new NN sublinear sequential, which implements the activation checkpointing. Some results are shown on the right for ResNet 9 from Homework 4 and a newly implemented VGG 11. We see solid memory savings at the cost of increased runtime.